Tomoki from Jungshi. Yes. Go ahead.
Hi, I'm Tomoki from Tohoku National Johnson University. Today, I'd like to talk about cosmic ray acceleration in magnetar transit. This talk is based on these two published papers and collaborator is Jiro Shimoda at University of Tokyo. Let me start with the observation of ultra-high energy cosmic rays. Let me start with the detection of Amateras particle. This is second highest energetic cosmic ray from the universe. And its energy is about 200x electron volt, which is about 2 times 10 to the power of 20 electron volt. And this left panel shows the observed cosmic ray spectrum, and Amateras is at the edge of this spectrum here. And using this energy, we can estimate the mean free path of this ultra energy cosmic ray. And using this mean free path and intergalactic magnetic field model, we can estimate the source of this cosmic rays. And this right panel shows the source position of Amateras particles. As you can see, these sources are inside local void region. So there is no steady source candidate for this Amateras particle. It means this particle may come from some transient activities. Then, where and how is it accelerated is problem. There is other ultra-energy cosmic ray observations. This left panel shows the arrival direction of or source position of ultra-energy cosmic rays. And you cannot find hot spot in this figure here. And this right panel shows the composition of ultra-energy cosmic rays. In very high energy, the composition becomes heavier. It means the cosmic ray is not composed of protons, but composed of some heavy element like nitrogen or iron, that kind of things. So the question changes. Where and how these heavy elements are accelerated? This is the question of today. And in order to consider that question, let's start with Hira's conditions. In order to accelerate cosmic rays, the Raman radius of the cosmic ray should be smaller than size. Accelerated cosmic ray is gyrating, and if the gyro radius is larger than the accelerator size, then it will escape from the source. This is the same as accelerator on the Earth. And this right panel shows this relation, and above this line, this object can accelerate cosmic rays. And you can find some AGN or AGN jet here, but as I mentioned, Amateras particle came from local void region, so there is no good candidate for this. No good candidate in these regions. So, but when we see this figure carefully, we can find another candidate for the accelerator. This is neutron star. And so, galactic or extragalactic neutron star may accelerate ultra high energy cosmic ray in this local void regions. And when we observe the accelerated particle, we observe Amateras particles. So if we assume this neutron star scenario, the question changes: how to accelerate nuclei in magnetars? Okay. So far, some people make some theoretical models of cosmic ray acceleration in magnetars. Mainly there are two scenarios. One is shock scenario, and the other is electric field scenario. In magnetar bursts, outflow is ejected from the magnetar, and it may create shock at outer regions. And heavy element can be accelerated in this shock region by diffusive shock accelerations. One good point for this scenario is this acceleration is associated with some bursting activities of magnetars. But negative point is we don't know how much heavy elements are. How much heavy element exists in this output. This is a good point and bad point of this shock model. And the other is magnetospheric electric field model. Because neutron star is spinning, it induces electric field at the surface of magnetars. And this electric field can accelerate heavy elements directly from this surface of magnetars. And the good point of this magnetospheric electric field model is they accelerate element from the surface of magnetars. So heavy elements are naturally accelerated in this scenario. But if we follow this scenario, then a very, very fast spin of magnetite is required. Magnetars are spinning with a spin period of about 10 seconds or so. But this scenario needs a spin period of about 1 millisecond or so. So this scenario requires very, very fast spin compared to observations. So what we need is very good scenario that we need another scenario for accelerations. And in our work, we consider cosmic ray acceleration in magnetar bursts, and it directly accelerates cosmic rays from the surface of magnetars. This is what we need in our work. And our work is based on these movies. This is the spinning top in the ISS. And when spin top rotated in ISS, the spin axis, the direction of the spin axis suddenly changes from left to right, right to left. This is nothing special, but one of the solutions of this kind of equation of motion of rigid bodies. So what happens? Let's consider what happens if this motion realizes in magnetars. This is the starting point of our scenarios. The magnetars can be triaxial due to its magnetic field or some mountain. So this kind of shape is naturally formed in magnetars. And based on this assumption, we solve the motion of magnetar spin. We just solve these Euler equations, and this black arrow shows the the direction of spin axis. And neutron star is rotating around this axis very fast. But when we wait for about 100 years, then the direction of this spinning top changes from up to down. This is completely the same as the spinning top in ISS. And during the spin flip, sudden inertial force is induced at the surface of magnetars. This force is called Euler force, and this sudden Euler force can break the force balance at the surface space of magnetars and make some fractured region at the surface of magnetar. And from this kind of fractured region, electrons and ions are ejected from here. And in addition to them, the internal energy of electrons at this region can be summarized and resulting in the hot plasma creation. And if this hot plasma is created, then X-ray can be emitted from that plasma at this region. This right panel shows the relation between the size of fracture and available energies for X-ray burst. And if the fracture is larger than about 7 meters, then naturally observed magnetic X-ray burst energy is explained. It's typically about 10 to 36 to 10 to 40 or so here. this is the scenario for X-ray emission. And in addition to X-ray emission, we can also expect ultra-high energy cosmic accelerations. And after the onset of the burst, electrons streams freely along these magnetic field lines. Here is the surface of magnetars, and here is outside. Electrons escape freely from surface to outside. And these ions try to catch up with electron streaming. However, ion streaming is delayed by ion-ion collisions. So, at the very onset of this burst, charge separation occurs because electrons escape faster than ions. And ions there's charge separation between plus and minus here. As a result, strong electric field is induced at the surface of magnetars. And this electric field naturally accelerates heavy ions from the surface of magnetars. And when this accelerated ion escapes, it will be observed as ultra-high energy cosmic ray from magnetar transient. And when we estimate the maximum energy for these ions, it's about 10 to the power of 21 electron volt. And this is 10 times larger than Amateras particle. So this scenario can explain the energetics of Amateras particle. And if nuclear separation occurs above these acceleration regions, then neutrons are ultra-high energy neutrons are also created from magnetar transient. And we name this kind of burst as instant jet ion acceleration in opposite magnetar origin burst called ISMO. This is pronunciation in Japan, but this is we call this as ISMO burst. Okay, this is output spec. From magnetar transient, we can expect ultra-high energy nuclei and ultra-high energy neutron, and possibly it makes neutrinos, and we can also expect X-ray emission. And time and positional coincidence of these events are good to check this scenario, and we need more detailed calculation for check event. Okay, here is summary of my talk. Thank you very much.
Questions?
Triggered by sudden fleet.
Sorry.
Burst are triggered by sudden fleet.
Yes, in this scenario.
So it's a 100-year physical time scale between two concentric bursts.
It depends on the deformability of magnetars.
So can you explain the waiting time scale between two bursts?
For it about the order of year to 100 years.
Okay.
And we know the tidal deformability of magnetars by gravitational observation, gravitational wave observation, or pulsing observation. So using that information, the event rate is about 1 per 100 years to 1 per 1 year for single magnetar. Okay.
So you mentioned ion-ion collisions.
Yes.
So can you suggest how much this ion-ion collision dominance is? Because the magnetic field is so strong that there may not be collisions, or the ions may be aligned toward the magnetic field.
When we calculate the not optical dips, collision rate, then it's very much higher than dynamical time scale. And it's so ion collision naturally occurs at this region, and in detail, this ion collision may regulate determines this maximum energy. So ion collision is inevitable in this kind of system.
Even the magnetic field is so strong, these collisions are inevitable.
Also magnetic field is very strong. ions don't feel that kind of strong magnetic field because of their large inertia.
Oh, okay, okay.
Electrons just move around magnetic field, but electrons don't care about magnetic field.
You have one quick question?
I was just wondering if you thought about other features from this spin flips, such as the gravitational wave emission or something like that.
Yeah, gravitational wave is also expected to be and some very old paper study this kind of
Okay.
detail.
All right, let's thank the speaker again.
Okay.